Recently, in my performance-aware programming course, I mentioned some things about how page faults will change the speed at which you can use memory the first time as opposed to when you recycle that memory. And it's just something that you kind of have to be aware of when you're taking performance measurements or when you're designing things that you're going to do in software. The first time you provision memory from an operating system, there are extra costs there. Now, a lot of people didn't know that, and they also didn't know why that was the case. And so what we ended up doing is several additional videos that explain how the VM subsystem in modern CPUs and modern operating systems actually work. This turned out to be something that people were really interested in, and so it was kind of a fun little excursion where we looked at some various things and how we could test to see what the operating system was actually doing with pages and stuff like that. What I wanted to do here at the end as a wrap-up to that little sort of unplanned excursion, and also release for free because I know a lot of people probably don't know some of this stuff, is just show some techniques that are actually very easy to accomplish with the virtual memory subsystem of the CPU and modern operating system APIs that would be extremely difficult to do any other way. In fact, sometimes it's actually just impossible to do, so people wouldn't necessarily think that they can even do it because it wouldn't be possible to do by hand, but actually by using the VM subsystem, you can totally do it. Let me start with the first one, which is the most common one that you'll see. You may have seen this one before, although a lot of people haven't even seen this one, and it's a really kind of wild one. That is circular buffers. Now, normally, when we want to implement something like a circular buffer, what we're talking about is like, well, okay, I've got, some buffer here that's, 16K. And I want to be able to pretend like it just kind of goes continuously and wraps around back to its own beginning, right? Typical use of this might be like a scroll back buffer or a send and receive buffer or something like that, where you're kind of trying to reuse the same memory, but you're trying to move through like a data window or something like that. Well, what we typically do is we just pretend that this same 16K is like repeated both before and after the actual buffer. But of course, since that's not what's actually going on in actual memory, what we have to do is have some kind of like utility functions or a class or something that the user of one of these buffers actually calls through to do their reads and writes. And what that class tends to have to do is it has to go, okay, if I wanted to do a read like this, where the person is trying to read this much out of the buffer, and we're trying to pretend that it wraps, well, we've got a problem because this part goes off the end of the buffer. So actually, we need to give them back this part here, welded to this part here. There's like a gather step. So what we actually have to do to produce this, right, is we can copy this part out from here, and then we have to copy this part down from the beginning of the buffer to produce the actual chunk that we're going to hand back to the user. And the same process has to happen in reverse when they go to write. If they try to write into the buffer and it's going to straddle it, let's say maybe they're writing back, behind here and coming in here, it has to do things like pick up this part of the write and splat it back down to the bottom. So all that stuff has to be hand-coded. There might be bugs in it because maybe, you've got to debug that as well because it's kind of finicky code, and you have to make sure everyone calls that, because if anyone actually tries to write to this without calling the circular buffer stuff, it might break, right? You might have crashes where you go off the end, or worse yet, if there's just some other memory there, it'll overwrite it. It's just, right? It's not great. It's a lot of extra work, and it's error-prone, and it's inconvenient. It can't even be used with existing code, right? Because if that code wasn't previously using a buffer method which had this sort of read-write kind of API to it, you can't even pass them one of these buffers. You will have to rewrite that code to use this, and that's a huge pain as well. Worse yet, what if you don't even have the source code, if it's just a binary? Well, all of those things are non-problems if we actually take advantage of the built-in virtual memory system inside x64 CPUs and Windows, or equivalently on ARM and Linux. It really doesn't matter. This is pretty much standard in most operating systems and CPUs now that are on consumer hardware. What we can do instead is actually just create an actual automatically repeated buffer in memory. Now, the reason we can do this, and I went over this in detail in the course, so I'm just going to mention it briefly now, is because actually pointers on x64 nowadays, and there's an equivalent thing for ARM, is a packed set of things that are used differently. It's not just one big number. A pointer is actually a 12-bit offset that is used to offset in physical RAM, but it's only 12 bits, so it only has 4096, range. And then 9999 4 separate 9-bit indices. And there's nothing in the top, just zeros there. Well, these 9999s here, what they actually do is they index into a tree-like structure that's in physical memory that tells the CPU what physical memory corresponds to your pointer addresses. Your pointer addresses are just made-up numbers that are in your virtual address space that don't actually mean anything when we go to look at the physical RAM of the machine. Instead, it uses a 4-level paging structure. It takes this top index and it looks it up in a table, and then it takes the next index and looks that up in the table. It basically it finds the table it's going to use by looking up the first one. Then it takes the next one and the next one. And finally, when we've done that 4 times, we've looked up at a table to get a table, we look up in that table to get another table, we look up in that table to get another table. Finally, when all that's done, we look in that table, right? And that's where we find which physical RAM page we're actually going to go to use our 12-bit offset to get an actual byte. It really does happen that way. It's cached in a thing called a translation look-aside buffer, but it really is doing that. Now, what this means is that at the 4K level, from 0 to 4096, 4K is worth, we can't really do any remapping. Each 4K chunk of memory pretty much has to be mapped to a specific 4K chunk. But there's nothing to stop us from mapping multiple 4K sections of our virtual address space, the thing that our pointers are actually in, to the same physical RAM. So if we think about what happens with our virtual and then our physical address spaces, our virtual address space can very easily have this 16, 16, 16 structure here, as if there was actually 48K of continuous memory broken up into 16K chunks, as we're sort of thinking of them. So this 48K in our virtual address space can exist just as it is, but each of these chunks can all be mapped to the exact same 16K of physical memory. What this means is that the CPU itself already has all of the logic in it that's necessary to implement a circular buffer. We don't ever have to code that because Intel already did that for you. Or if you've got a Zen chip, AMD already did that for you. So the CPU is already remapping all of your pointers through tables anyway. We might as well just use that and get better performance, less bugs, and more flexibility, essentially for free. So if we look at what we need to do this, it's really pretty straightforward. We just have to ask the operating system for 48K of virtual address space and then tell it to map each chunk of that to the same physical buffer. Now again, there are some limitations. The allocation granularity of the operating system, which we know has to be at least 4K, but it could be higher on Windows at 64K, for example. We may have to round our buffer sizes up to that. So for example, if we wanted a 16K buffer, we may not be able to do that on all operating systems. We may have to use like a 64K buffer, for example, or something like that. It depends on the operating system, it depends on the chip. But as long as we're allowed to do that, as long as we don't need a very specific buffer size, we could use any multiple of 64K, for example. So n times 64K, any buffer size that looks like that, 128K, 256K, whatever, all of those buffer sizes will work. And all we have to do is set up our page tables so that it maps repeatedly into memory like this. And we don't have to stop at 3. If we wanted to, we could map this same buffer multiple times before and after us. We could have 3 buffers worth behind us and 15 buffers worth ahead of us. If that's how our algorithm wants to work, we could do that. Now, it is a little janky on Windows. The APIs are not as smooth as you might like, but it actually is still pretty simple. If you're on a modern version of Windows, like Windows 10, a recent version, or Windows 11, then there's actually an API called virtual alloc 2 and map view of file 3. I know the 2 and 3 are kind of crazy, but using these 2 APIs, you can basically reserve your 48K or however much the total mapping size is that you want. You can reserve it. Then you can say, okay, I would like to map the same one buffer to each of those. And you can do that directly. If you don't have a modern version, so you're working on a very old version of Windows 10 or on previous versions, Windows 8, Windows 7, then you actually have to just use regular virtual alloc and regular map view of file ex. And these are slightly more error prone. You have to try them a few times because in theory, someone could sneak in and steal an allocation from you. This is because these new APIs introduce something called a placeholder, which allows you to do things like allocate virtual memory space, but then use it for file mappings afterwards. Now, you may wonder, why do I keep saying file mappings, and why is the API map view of file? There's no file involved here. Well, it turns out that's just how Windows refers to anything that you're going to be doing to map memory in this way. So even though there's no file backing this thing, unless you count the operating system's actual page file, for example, even though there's no file involved, we still have to use that API. So our file mapping object actually doesn't involve a file at all. That's just a way of referring to that buffer chunk that we're going to use. Now, I know this is kind of a whirlwind. Again, this is not meant to show you every last little detail about this. This is just to familiarize you with these techniques and that they can occur. And of course, in the course, we go over a lot of this stuff in detail. So if you want to know more about it, that's where to look. But for now, let's go ahead and look at the actual source code and watch it run so we can see how this virtual buffer stuff works in practice. And again, you don't have to limit it even to circular buffers. You could map anything you want in this way. So you can have like random repeating sort of different buffers that go in random orders as you go through them. I don't know why you would want to do stuff like that, but pretty much anything you want to do that involves mapping things at a granularity of either 4K or 64K or whatever the granularity is of the thing you're working on, you can actually do. So let's take a look at that now on the computer. In listing 121, I've written some example code that shows how to do this circular buffer stuff. There's a lot of kind of random Windows things that have to happen here. In fact, it's pretty much all random Windows API usage just to get the page table set up properly. But the concepts, as we saw on the lightboard, are quite simple. The sort of Windows stuff we have to do here is, first of all, because the new way of doing the allocations requires us to look to see if this version of Windows actually supports it, there's some nonsense here that we have to do that's kind of ugly. This is basically just putting in Windows SDK stuff in case the version of the SDK is not new enough, and we have to get some functions that we can't guarantee will actually be there. So again, just kind of annoying stuff because the Windows API is new and we can't guarantee that we're building with an SDK that has it or running on an operating system version that has it. I created a circular buffer type here, which we can use to allocate one of these, and here are some simple utility functions that it uses. Is valid will tell you whether or not you actually got back one that has any memory or whether the allocation failed, like maybe you asked for too much memory or something like that. There's rounding to the page size, which we have a utility function here for. Then there's some things to deallocate them, which of course require deallocating multiple pieces because it's going to be mapped repeatedly. But these are really just pretty simple little things. The main part of the code is just this allocate circular buffer call. The way this works is you pass a minimum size, which is how big you want the buffer part to actually be that's actually holding data. And it's called minimum size because it might have to be rounded up because again, it has to be rounded up to an even multiple of the allocation granularity for Windows. You could try to round it up only to the page size, but like I said, I haven't really tested that, so I'm not sure how compatible that really is. Rounding up to the allocation granularity, on the other hand, is very portable from what I've seen. So you pass a minimum size that will get rounded up right here, and you pass a repetition count, which is how many times you want this buffer mapped. So 3 for a typical circular buffer, 1 for reading before, 1 for reading after. But if you wanted even more wrapping, so you wanted to be able to look back, say 2 or 3 times the length of the buffer and still get a repeated buffer, you could pass a higher rep count here. I just made the routine allow you to map it as many times as you want. So first thing we do is create one of those file mapping objects. Again, this is something that you create in Windows when you want to map a piece of memory multiple times. And you can see here what we're doing is passing in the data size, which is 64-bit. And of course, Windows, this is an old API. So we have to pass it in 2 chunks, the high 32 bits and the low 32 bits, but we're really just saying what the size is. We're saying here that we want to be able to read and write from it, of course, because it's a buffer, we want to do both things to. And then you'll notice that these other things don't actually specify anything. The reason for that is, again, we're not actually creating a real file mapping here. What we're doing instead is just creating a dummy size that we're going to use to say we want to map the same physical memory multiple times. As I mentioned on the lightboard, it's a bad name for an API. It comes from the fact that this was originally used for doing memory mapped files. Assuming we were able to get that file mapping from Windows, we then have to go ahead and do the work of figuring out whether or not we have access to the new APIs. The new APIs are virtualalloc 2 and map view of file 3. Not very creatively named. They are just new versions of those same functions that provide extra functionality. functionality. Assuming we get them, we take the new, more modern path. As you can see here, what we do is we call virtual alloc2 with the total amount of size we want. So this is the size of the actual buffer times the number of times we want it mapped. And you'll notice we do not commit this memory. We just say we want to reserve it and that we also want to use a placeholder, like I said. Then we're going to do a loop for as many times as we want the buffer mapped. We first free the reservation that we did for this part of the mapping. So it's just one buffer size worth. We free that, but we use this mempreserve placeholder to say, Windows, we're freeing this, but we're going to use it. So actually don't quite free it, right? Like I said, it's a little bit weird. We then call map view of file 3 and say, please map that same chunk that we created up at the top there, map that same chunk to this address region, please, and replace that placeholder that was being held here. So that's all we do. And we do that for every time we want to map it. So again, just to restate this here, we create the file mapping for the buffer size, which is basically saying this is how much actual physical memory we expect this thing to be mapped to. We then allocate the entire virtual address range, which could be much larger because it's multiplied by the rep count. We then loop through, and for every time we want this buffer mapped, we free just one buffer's worth at the location we're trying to map. Then we do a mapping at that location. And when we've done that for every repetition we want, we are done. And that's the new way. The old way we do if we don't get access to the new functions. And the way this works is we just sit in a loop that tries to do the allocation as many times as you want. I picked 100 here. It's purely arbitrary. It's just how long do you want to spend trying to get this circular buffer? Usually it will work on the first go. But if it doesn't, how many times do you want to repeat it? Who knows? The way the interior works is very similar. We go ahead and do a virtual alloc for the entire size. We only reserve, though, we don't commit. That's because, again, we don't actually need all this memory. We just need this much virtual address space. Assuming we get it, we virtually free it to give it back to the operating system because it needs to not be marked as used in order for map view of file to succeed. We then go through, and for every time we want the buffer mapped, we call map view of file with that location and the size of the buffer. And that's basically it. This is actually simpler than the above version, but of course, like I said, it has the drawback of in between this virtual free and all of these calls to map view of file ex, it is technically possible for some other thing in your process address space to call virtual alloc and steal that memory range away. So you can't guarantee that it will work, hence the wrapping in a number of attempts just to make sure that it tries pretty hard to get one. Now, does all this work? Yes, it does. Here is the main that I made for this. It prints out circular buffer test. It allocates a buffer size of 64 pages or 256K. It calls the circular buffer allocation and asks for it to be mapped 3 times. It then goes ahead and sets up a data pointer as if it was going to use this buffer as something that was pre-mapped and post-mapped, just like we drew on the board. One whole buffer before the buffer and one whole buffer after the buffer. And it does that by taking the place that we allocated and advancing by exactly the buffer size. So we're right at the start of the middle of the 3 buffers. We then write to the very first byte in the buffer the value 123. Then, to prove that our circular buffer is actually mapped circular, we then print out what we see at the entire buffer size backwards and the entire buffer size forwards, as well as the part we actually wrote to. If we go ahead and run this now, what we can see is that at all 3 locations, we print out the value that we actually wrote, even though we only wrote it to just this middle location. Again, super cool. The virtual memory subsystem of the CPU just takes care of this for us, so we magically get all of our writes replicated to all 3 buffers, even though we only wrote to one of them.
Circular buffers are one of the most commonly cited things you can do by monkeying with the page table like that, but actually there are other things we can do with the page table that are perhaps not quite as glamorous, but are very powerful when you look at the kinds of things that you can do with them. One of the other really interesting things about x64 page tables is there are dirty and accessed bits per page. Now, we didn't really look at this kind of thing because we are not really capable of looking at the actual page tables in Windows on user mode. These are things that only the kernel gets to see, and we're not really allowed to read and write from them. So there's only so much I could really show you about how the page tables are working without doing something like writing a device driver or something like that. But The x64 page structure, if you remember, I said there were 64-bit entries in there, and obviously you don't need 64 bits to refer to the physical RAM of the machine. The physical RAM of the machine, as we already know, is at a minimum going to be referenced in 4K pages, so you already have 12 bits that you know you're never going to need because those are coming from the actual virtual pointers, so the page table itself can just talk about 4K chunks. So there's plenty of room in a 64-bit page table entry for other things. And as we mentioned, some of those things we already kind of know what they are. There are things like whether or not this page is allowed to be written to or not. That's how the operating system can do things like read-only memory or copy on write and things like that. But it also has dirty and accessed bits. These bits are set by the memory management subsystem in the CPU, such that anytime there is ever a use of a particular address, meaning the address translation layer has translated an address and touched this particular page table entry in walking it, the access flag will be set, or so says the manual. Like I said, we can't see these things in userland, but that is what's supposed to happen. And anytime someone uses a particular address for a write, using a particular page entry for a write, the dirty bit will be set. What this means is that it's actually very easy for a kernel mode thing, for something which actually can use the full power of the CPU and has access to things like the actual data in the page table, to know where you have read and where you have written. Now, if you think about what this means, things that might sound completely impossible to do cleanly without a lot of re-architecting can suddenly become a lot easier. If you are given a program that you can't really even modify at all except perhaps just the memory allocator part of it, you can actually make something which knows all of the pages of memory that it has touched at any time. So you could do things like recording and replaying back things that happened in this application just by saving and restoring memory based on what has been touched and what hasn't. All sorts of things like that open up when you have this ability to do dirty bits. And just to be specific about what happens here, if we imagine that last level page table where we have a bunch of pages here, in this last level page table, this is the fourth 9 in that set of 9s in the pointer. Well, if we take one of these and that points to some 4K physical page here in RAM, what happens is you have to imagine there are these little dirty bits here. And anytime the CPU goes to commit a write to one of these pages, it's going to fill in the dirty bit and say, someone wrote to this page. Now, the reason that we have this is because operating systems are trying to optimize what they swap in and out of memory. And if you think about it, an operating system doing virtual memory support where it writes to disk and reads back memory from disk when it exhausts the amount of physical RAM it has, well, this is very handy because it knows when it goes to page out some memory, if the dirty bit isn't set, it doesn't have to write it to the drive, right? If it hasn't been written to since it was actually originally read in from disk or created as zeros, then you don't really have to do anything with it. It can just be vaporized, and when you restore it from disk, the old version that you restored last time is still just as good. You don't have to rewrite it. But operating systems now export the ability to read these things directly. On Windows, there is a thing called GetWriteWatch. This API will tell you at any time what all the 4K pages are in a particular memory allocation that have been written to. It will also reset those particular dirty bits to be non-dirty, to be clean, so you can do this periodically. As your program runs, you can call GetWriteWatch, find out all the pages that have changed, save out those pages to a log if you wish, and clear the dirty bits. Run some more, do the same thing. This allows you to produce basically a memory replay of any running application effectively for free. The only thing you have to do is intercept that memory allocation layer because the allocations have to be marked for write tracking. It's just Windows requires you to add a little flag in there. And then you just need to call GetWriteWatch at regular intervals. It really is that simple, and it's all done basically for free in the page tables because this is already happening anyway. So you're not even really incurring any kind of huge overhead. You don't have to write through special pointers or use some kind of utility function to do all your commits or anything like that. So let's go ahead and take a look at what that looks like in practice, because it's actually incredibly simple and, like I said, very powerful for writing utilities that take a look at how things are using memory, or to be able to help debug by recording the memory that's actually being used. Here in listing 122, I've created some example code that does the write watches. You can see here we have a thing called an address array that I made, which is really just a way of returning what the written pages were. We need some way of saying, here are all the pages that were touched when we do that check. Then I created something called a tracked buffer, which is just something that has a simple buffer in it, like we've used throughout the course, but it also has this results array that it can use to communicate to you which things have been written to. Besides the simple deallocation and the is valid for checking to see whether it actually succeeded when it allocated, really all there is to it is an allocate tracked buffer call, which you give a minimum size and it will allocate the buffer for you, and get and reset written pages, which is something that will tell you where the writes have happened. Now in allocate tracked buffer, it's fairly straightforward. All we do here is see how many pages this actually uses. So we take the size and we do a divide by the page size, rounding up, because of course, if you ask for something that doesn't end directly on a page boundary, you will be allocating one extra page than this would return. So that's what this is designed to do here, just make sure we get the full page count. We then go ahead and allocate the actual buffer, which here you can see will be however much size you asked for. And the only difference here is we pass mem_write_watch. That's the thing that will let Windows know we expect to be reading the dirty bits out of this thing. We then also allocate some extra space here that is not write_watched, and that is just an array for storing these results. That's about it. That's really all there is to it. Now, anytime we want to know whether any of that memory has been written to, we can call get and reset written pages. And what we do is we call get write watch, which says, here is the memory range that I had allocated before, and here is that buffer of addresses that I'd like you to fill out. Tell me all of the things that were changed. It will also tell us what the page size is that it was using, so we can figure out for each of the addresses it gives back what is the range that the write might have happened in. And then we also use write watch flag reset, which says reset all the dirty bits because I only want to know what has changed in between calls to get and reset written pages. That's really all there is to it. I added a little print address array function here that just says what all the pages are that were written to, but that's it. Now in our main, which you can see here is a very simple test. We allocate a 256 page buffer to play around with, assuming that we actually get one, meaning that there's enough memory in the system to have this and that it supports write watching. We go ahead and just write to a bunch of pages. Here I wrote to page 15, 25, 35, 45, and 55. We call this pass A, and then we write out all of the pages that the operating system told us got written to. We do this a second time just to prove that the reset works, and we write out to a different set of pages. So if this write watch works, then in this entire giant buffer that we allocated, it will properly tell us that page 15, 25, 35, 45, and 55 got touched on pass A, and it will tell us pages 11, 22, 33, 44, and 55 got touched on pass B. And you'll notice we wrote to page 11 twice here, but we only expect to see that show up one time because, again, the write watch only works per page. So if you write twice to the same page, we're only really going to still see one write notification for that entire page. If we go ahead and run this, what we see is we get exactly that. On pass A, we see only the pages that we touched in pass A, and in pass B, we see only the pages that we touched in pass B. So again, the operating system telling us exactly which of these 4K pages were touched and exactly when they were touched, meaning that in between those calls to get write watch, the pages it will return are specifically those that were written to only in between those two calls. So circular buffers and, write tracking to memory, those are both really cool, and they're things that you'll probably want to play around with that can actually give you very powerful results in things because they don't really affect anything else in the program. It's sort of this magical little VM stuff you can do at the CPU layer, and none of the rest of the code has to be aware of it. You can use code that has no idea it's working with circular buffers, that has no idea it's being write tracked. And so it's a very powerful subsystem. Now, there's another thing that it can do that's also something that is not very well known, even though it's kind of obvious once you know how page tables work. And that is sparse memory. Now, normally, When you see people talk about things like growable arenas or stacks or things like that, we kind of understand now, because we've seen how page tables work, how you could do things like have stacks in your virtual address space that don't actually take up very much memory until you actually use a lot of them. So for example, if we want to have some contiguous memory, guaranteed to be linearly contiguous in our virtual address space to store, say, a gigabyte of some stack, well, that 1 gigabyte only has to be in the virtual, right, address space. It doesn't have to be physical. It can just be virtual. So there's a lot of 1 gigabyte chunks in the virtual address space. As we know, we have like 48 bits worth of addressing that we can use. We don't quite get 64 bits, right? Obviously for, specific reasons, but there's a fair bit of virtual address space available, so we can have lots of 1 gigabyte chunks. In fact, we can have way more than there is memory in the actual machine. If we want to, we can reserve lots of 1 gigabyte chunks, and those 1 gigabyte chunks maybe we only use a little bit of. That's the standard way that you see people use this sort of like only commit on demand sort of thing. And what this basically amounts to is saying something like this: reserve all of these page table entries, but only map one of them to a 4K page, right? And then we start filling it up with stuff, and only when we see that we're gonna need another page do we actually go and map a new one in here and take another 4K. And we can just keep doing this as we go. That's typically how stacks work when you use virtual paging like this, the 4-level paging structure to implement a stack. This is how you would do it. You just make sure you reserve large runs in the page table, so you are wasting a little bit of page table space, but of course page tables aren't that big. And you never actually use very much RAM at all, because you don't actually have to store any of this until you fill up enough of it. So you can reserve lots of 1 gigabyte chunks of the page table, which of course is, not 1 gigabyte, it's 1 gigabyte divided by 4K. You can reserve lots of those chunks in the page table, and then you can just commit on demand. However, this gets more powerful when you stop thinking of it just as a stack and start thinking of it as sparse memory. Because there's no reason we have to fill this up in order. Let's suppose, for example, we want to have a table that is, 64 gigabytes large. It's just a massive table. And our machine may not even have 64 gigabytes in it. It might only have 16 gigabytes or 32 gigabytes, or even if it does have 64 gigabytes, well, we probably can't use all the memory in the machine just for our table. But we don't have to. What we can do is reserve just 64 gigabytes of virtual address space, which does sort of black out a huge amount of our page table. So we are paying some price for it. But we can then only commit the pages that we actually need. If we know that we're only ever actually going to use about 1 gigabyte of this 64 gigabytes because most of it's just going to be 0, then we don't actually have to ever commit this 64 gigabytes of memory. We can just pigeonhole commit little tiny parts of it. So we can have a allocated space whose addressing is linear and actually going through the translation look-aside buffer as our sort of hashed acceleration, right? But actually, we've never used anywhere close to 64 gigabytes of memory. So we could actually have, more than one 64 gigabyte table even potentially, depending on the situations, as long as they all use a fairly small amount of actual memory. They will all be resident at the same time. They'll all be fitting in physical RAM, even though they're nominally 64 gigabytes. So again, we can do this on Windows. That's the difference between reserve, which gets virtual address space, and commit, which actually has to say, okay, prepare to store this, so it's going to need room in the page file and so on, right? As long as we reserve how much we want, but only commit what we want to store, we can effectively have sparse memory. Here in listing 123, I've written some example code for sparse memory, and it's pretty straightforward and simple. All we do is our sparse buffer here. I created it just because, hey, you probably want to have something that you pass around to represent this sparse buffer if you're going to use it, but really you don't even really need it, you just need the addresses. We can check if it's valid, we can allocate one. All we do here that's different from a normal allocation is we just pass memreserve and page no access, because all we're doing is creating a reserved set of our virtual address space. We're not actually asking the operating system for any actual memory yet. Assuming that we get this, we just remember it in the sparse buffer and off we go. Of course, the allocating is the same as always, we just release it, but the crucial difference here is this thing called ensure memory is mapped. When we actually want to use a part of our sparse buffer, we can call this if we don't think that that area has already been set up for use, and we then just call virtual alloc again with whatever the pointer is where we intend to write. We give it however many bytes we expect to be using at that location, and then we say we would like to commit that memory now, and of course we want to use it for reading and writing. That's really all there is to it. If we then look at our test, all we do is we say, look, let's allocate a absolutely gigantic buffer, 256 gigabytes. This machine doesn't even have 256 gigabytes of physical memory. So it literally couldn't have a buffer of this size stored. It's not possible. However, because we're only asking to reserve that in our virtual address space, the call actually will succeed. Then we can go ahead and write to offsets that seem ludicrously large. 200 gigabytes in, we are going to touch in this buffer. But again, because it's sparse memory, it doesn't matter that we can't store that much stuff in RAM because we're never actually going to try. We're only going to map certain select pieces into RAM, and the rest is just managing our virtual address space in the page tables. So we loop through the offsets, in this case there are 4 of them. We write to each of them by saying ensure that the memory is mapped first, and then write something to the offset. We write specifically 100 plus whatever the index is, so we would expect to write 100, 101, 102, 103. We then go back through just to prove that it worked, and we read from each of those offsets and print it out. If we go ahead and run this now, what you can see is that it works exactly as if we really had a buffer that was 256 gigabytes worth of storage. Now, of course, we don't have that, and if we go to the actual performance monitor here, what you can see is that we only have 32 gigabytes of memory on this machine. But the 4-level paging scheme allows us to still act as if we have this 256 gigabyte buffer as long as we never use the entire thing at once. If we only use pigeonhole pieces of it, i.e. sparse memory, it will just work.
So as you can see, there are actually very powerful things you can do with the virtual memory hardware that you have access to if you just know where to look in the operating system for calls that allow you to manipulate it. Things that might be incredibly difficult to retrofit code to do, or that might take you quite some time and be error-prone or inefficient to implement by hand in a system that actually has to do this manually, can be made trivial and simple to implement just by using the existing virtual memory hardware, because everything you do in the CPU is already going through these translation tables for every address, and so you might as well take advantage of it to work to your benefit, either to track writes or to remap how memory is looking, or to do things like use address ranges that are larger than what you can store. All sorts of things like that are possible once you understand how that system works. Now, of course, if you like this kind of stuff, this is what we do over at computerenhanced.com. You can go ahead and check it out. I also included over there a 4th thing, which really isn't part of these tricks. I didn't really think of it as a virtual memory trick, but when we were going over this stuff in the actual course, people asked some questions about could they use 32-bit pointers even in a 64-bit address space? And of course, you actually can do that. It's not necessarily really a VM-style trick, but because you can just restrict the mapping to the lower 4 gigabytes, there are actually ways to do this so that you can just use 32-bit pointers even though you're in a 64-bit address space, and mix them freely so you can still be using 64-bit pointers as well. This actually does work, and I included a listing for that as well, just as a bonus because people had questions about it. I thought I would show how you might create such a thing. So I'm not covering it here in the video, but it is with the listings over on computerenhanced.com if you want to check them out. So that's about it. Next week in the course, we'll be back looking at actual performance stuff for the Haversine problem that we've been looking at, and we'll be taking a look at how we can eliminate some of those page faults that we actually are starting up with for our file reads, and then we'll be moving on to looking at how the CPU transfers memory and whether or not we think that our file reads are actually going as fast as they should when they are cached. So that stuff will be coming next week. Until then, have fun programming, everyone,
and I'll see you on the internet.